Yeah, that's good. Philip is our
I'm the geek.
website administrator. Yeah. Yeah. So no, but it's been fun, I think, doing all of these.
Yeah, I feel like it brings the community together, and you know, in this time to like having this online thing, I think is a nice way to like bring communities together that that otherwise would only see each other once a year or something.
Yeah, that's true. But I think actually there has been a bit, I mean, there's been so many, because many different, I mean, all of a sudden you can go to any talk in the whole of Europe or in the whole of world. And often because they are in the, in the early evening or something like that, you don't always want to participate, even though you sometimes feel like you should. Yeah, but yeah, it's good. And also that often they are recorded, so you can get back to them later on. Yeah. Good, but I don't know if we should start to let people in, or we can wait a few minutes still.
Yeah, maybe we can start in 2 minutes. Vivi, I think it's fine. Yeah.
Sorry, I'm sorry for what I did.
It's fine, no worries.
Don't worry. He's still there. I just put him in the waiting room again.
Yeah.
I thought then we could talk more freely. I don't know. Yeah. Yeah.
So Tamara, you are in California, I'm correct? So
yeah, that's right. Yeah,
okay.
I'm in LA right now. I'm finishing my postdoc at Caltech and starting at Santa Cruz in July. So I'm really like right at the transition. I actually am stopping. My postdoc ends next week, and then I'm taking vacation before July 1st. So I'm like right at the transition right now.
Okay.
Yeah, I saw your email today. I don't know if you saw it.
Yeah, I'm at the weird time between emails. I'm trying to like remember to like use my UCSC email, but I keep sending emails from my Caltech email, and it's confusing.
Yeah, it is. Yeah, but it's good. Are you looking forward to your new position?
I'm really excited. Yeah, I'm really excited. Yeah. I have a PhD student that's going to start in the fall, so I'm like really excited for that, and yeah, it'll be good.
That's good. And you are moving also, or what?
Yeah, I'm going to be moving, but I'm going to wait until August to move, just because most of the time I've been in LA has been in quarantine, and so now things are opening up a little bit more, so just try to explore the city before I leave. But yeah, I'm gonna be moving soon too. But actually my family is in Santa Cruz, so I'm like not so stressed because I know I can always just like stay with them until I find a place. So
yeah. You will be the professor living in the basement of your parents.
Yeah, that's what my parents want. That's what they want.
Yeah. Well, it's so great that it turned out like this for you. That you, I guess this was the place you really wanted to go, right? Or
yeah. It's kind of it's a dream to like get to be somewhere in my hometown, and also like I'm really excited about the department too. So yeah,
that's good.
Nice.
All right, I'm gonna start letting people in, and then I'll just start the announcement at 4. Yeah. Okay, I think we're ready to start. Welcome to this week's Landscapes Live. And my name is Vivi Peterson, and I'm chairing the seminar today. And then we have as well Philip Stair and Boris Galiton as moderators of the chat and the questions after the talk. And we're very happy to see so many participants again this week. And we're now well into the summer block. And today we are lucky to have one of our early career talks by Tamara Pico. And Tamara, she did her PhD at Harvard University, finishing in 2019. And now she's been a postdoc for 2 years at Caltech before she will start her new position at University of California in Santa Cruz this summer. So congratulations on that, Tamara. And the title of the talk today is, it's on the slide here, In and Out of the Last Ice Age, the Influence of Glacial Isostatic Adjustments on Landscape Evolution in North America. And after Tamara's talk, you're welcome to ask questions and add comments in the chat that will open near the end of the talk. And you can also raise your hand if you would like to use your microphone. So for that, you can also just put an X in the chat and we'll notice you. And with this, I will simply give the word to you, Tamara. Welcome again, and thank you for getting up this early to join us here. And you have to remember to unmute yourself. I'm sorry.
Sorry.
I muted you before.
Thank you, Vivi, for that introduction. And thanks everyone for being here. I'm really excited to be giving this talk to more European or not US as much crowd. And all I had to do was wake up a little early. So thanks for being here. Today I'm going to tell 2 stories about landscapes and how these can be shaped over the ice age. So one story focuses on when ice sheets were growing, and I ask how rivers might evolve in response to solid earth deformation over the ice age, focusing on the east coast of the United States. And the next story is about megafloods, and we'll look at the role of solid earth deformation in ice age megaflooding in the Pacific Northwest of the United States. And for me, from a sea level background, what's fun about this work is thinking about how landscapes can represent new non-traditional measures of sea level, which might eventually become a new tool to gain insight into former past ice sheets. Okay, let's see. Bye.
So you muted yourself, Tamara.
Oh, I don't know how, sorry.
We hear you now.
Okay, I'm not sure how that happened. Okay, great, this is advancing. Okay, so sorry about that. So before I jump into my talk, I want to spend a minute on, I'm calling a diversity minute, on some of the other things that I work on in the earth sciences, and specifically on some work that's related to a secondary field of interest that I picked up during my PhD in feminist studies. So here are a few projects that I've worked on in this area. So I've thought a bit about first authorship, gender gaps, body metaphors in geology, and I want to speak to you specifically today about a curriculum project that I've been involved in called Geocontext. So I've been part of a team working on a curriculum project, creating a collection of teaching modules that provide a social and political context for historical and modern practices in geoscience. And I saw the Landscapes Live last week, and I saw Benjamin talked a bit about thinking about histories of our discipline. And I know Benjamin focused on the 1970s, and I'm going to talk even farther back into the history of our discipline. So part of the motivation of this project is that when we carry traces of the past with us through our cultures and practices, especially when we really revere certain parts of history without considering other sides. And so the goal of these modules is to incorporate different parts of our history as a discipline that have been excluded as relevant in the past, to help train the next generation of geoscientists to detach themselves from cultures and practices of exclusivity or oppression. So since this is the Landscapes Live series, I'm giving you a little taste of the module that's focused on geomorphology, which is one that I created. We all created different modules, and it's called Landscapes and Scientific Racism, and is about kind of how early landscape geologists were very involved in studies on scientific racism. And so I'm just kind of including little snippets from this module, and I encourage you to check out the full thing. But I wanted to include this bit about William Morris Davis, who I think is someone that we kind of cite as being, kind of a early modern geomorphologist, and kind of give a little bit of this context of the history of kind of social and political time that William Morris Davis was working at. So William Morris Davis was really passionate about education, and he wrote geography textbooks. And many of these geography textbooks included materials that connected topography and climate to the superiority or inferiority of different human races. So here's a quote from his textbook: "The study of physical geography gives the knowledge so that we may better understand the relation of man and nature. This relationship is of great importance because the progress of man from the savage towards the civilized state has been made by taking advantage of favorable geographical conditions." This next quote: "Few nations among Black, brown, red races have made important advances towards civilization. Inhabitants of North America were savages who did not know how to develop its riches." So we can see how these ideas of race and human progress motivated studying the Earth system. And William Morris Davis was influential to a number of other scientists and politicians that tried to explain perceived racial difference in physical, mental, and moral attributes by climate and geography. And this concept is known as geographical determinism or environmental determinism, and ultimately are connected to eugenics movements. And so this is kind of an example of material, well, from this specific module, and the idea of telling this type of story that kind of adds a context to the other stories we might hear about someone like the contributions of William Morris Davis, related to river captures or something like that, as that these stories serve as a counter storytelling that reframes the history of scientific discovery of geologic principles as a kind of outcome of a social and political time, and specifically kind of this projects that are rooted in colonialism or imperialism. And I think that these stories, more importantly, provide another angle to the unilateral training that we often receive in the geosciences, either implicitly or explicitly, about the social neutrality of science and the heroism of individuals that are considered the founders of our discipline. So in contrast to a scientific objectivity that's assumed to be value neutral, a strong objectivity requires us to understand the practice of science in a social context where the political, economic, and social values of the scientific community control the entire scientific process. So this was kind of just a little snippet, and I encourage you, if you're curious, to check out these modules or read the interview that we did that is in an EOS article. And I'm also really curious to know kind of these materials were designed for or somewhat US centric, and I'm very curious to hear your thoughts on how these might fit into kind of standards of teaching in Europe or in other places around the world. So definitely feel free to be in touch. So with that, I'm going to dive into the main part of this talk, and I'll just walk you through an outline. So I'm going to spend the first few minutes on the methods showing how I model the process of glacial isostatic adjustment, and I'll explain what that is. And next, I'll focus on the growth phase of ice sheets, or the last glaciation, and I'll explore how rivers on the United States East Coast may have responded to solid earth deformation as North American ice sheets grew rapidly late in the last glaciation phase. And next, we'll use these constraints on ice age deformation to learn more about the history of landscapes. And in particular, I'll show we can gain insight into the history of ice age mega flooding in the Pacific Northwest and the erosion of the channeled scablands using simulations of glacial isostatic adjustment. Okay, so we can model the process of glacial isostatic adjustment by understanding how the solid earth responds to loading stresses. So even though the Earth's lithosphere and mantle are solid, they behave differently in terms of rheology, depending on the time scale of the applied stress. So for example, during an earthquake, the solid earth acts elastically, but over long time scales, the mantle flows, so the solid earth can be modeled as viscous. On the glacial timescales, on timescales of 1 to 100,000 years, we redistribute weight over the surface of the earth by growing and melting ice sheets as we transfer mass between the ice sheets and the oceans. And this change in loading produces both an elastic or an instantaneous response, as well as a longer term viscous response. So in the sea level model that I use, I treat the lithosphere as elastic and the mantle as having both an elastic and viscous component. So the sea level model requires both an ice loading history, so the geometry of ice sheets through time, as well as earth structure parameters, including the lithospheric thickness and the viscosity of the mantle. And while most of my research centers on learning more about this ice loading history, I also need to prescribe the earth structure. And to do so, I use estimates of average lithospheric thickness or mantle viscosity in a specific region. And so in modeling glacial isostatic adjustment, I calculate the perturbation to the solid earth surface, the gravitational field, and the Earth's rotation axis in order to predict changes in sea level. And so here I'll define sea level as the difference between the equipotential surface of the ocean and the crustal elevation. So any change to sea level at a specific location includes changes to the gravitational equipotential and the crustal elevation. And I'll define this as relative sea level, since it's relative to sea level at that location today. And because we can measure the response everywhere on the Earth to a given change in loading, we can talk about a global pattern of sea level change. So here I'm showing present day sea level change due to glacial isostatic adjustment. And I'll point out some features here. So the areas in red are areas where sea level is actually falling. And for example, we can see over Canada here, there's this red region, and that's an area where the crust is now uplifting after the demise of the former North American ice sheets. So, and we can see there's this ring around Canada over the United States in blue, which is the peripheral bulge, which is now sea level is rising more than average as the peripheral bulge around the Laurentide ice sheet is collapsing. And I'm going to explain that in a little more detail soon. So this is the kind of physics that I use in my research and developing the results that I'll be showing you. So we'll jump into this first section, looking at United States East Coast rivers during the growth phase of North American ice sheets. So glacial isostatic adjustment refers to the solid Earth's response to the redistribution of surface mass loads as ice sheets grow and melt over a glacial cycle. So on the left, I'm showing a map of topographic change due to glacial isostatic adjustment during ice growth. So in this figure now we see the opposite, right? Because this is as the ice sheet is growing. There's this blue region over Canada, and that's a region that's subsiding as the ice sheet grows. So as the ice load grows, this region becomes isostatically depressed. And this red ring around the United States is the peripheral bulge of the Laurentide ice sheet, and it uplifts as the ice sheet grows. And so on the right here, I'm showing a schematic of how this works. As an ice sheet grows, it loads the crust, displacing mantle from underneath that ice sheet and forcing that mantle to flow outward to the periphery of the ice sheet, which then gets uplifted in what's termed the peripheral bulge. And so this peripheral bulge region is all kind of extends over the entire United States, and is where all these rivers on the US East Coast sit along. So, so here now I'm assigning some values to this map, and this change in topography that I'm showing during ice growth is a change in topography over about 15,000 years, from 36 to 20,000 years ago. So this is as the ice sheet is growing to its maximum load. So, so over Canada, the land is being depressed, and in the region around, these red regions are being uplifted up to about 100 meters on the peripheral bulge. And so what's interesting to me is that regions that were never glaciated can be uplifted by 10 millimeters per year. So these are areas that are very sensitive to the history of ice loading, but they've never had an advancing ice sheet scrape away their geologic record, right? So these are outside of the maximum extent of the North American ice sheets. So to me, that reveals the potential for these rivers to record surface deformation, since they're very sensitive, since rivers are sensitive to changes in slope. So through deformation of topography, glacial isostatic adjustment can move drainage divides and tilt slopes of river channels. And so I'm going to explore how the growth of the North American peripheral bulge during the growth of the North American ice sheets could induce changes in river evolution, and compare to 4 rivers that show evidence for a change in river dynamics during this time. In the 4 rivers where stars are shown here, glacial isostatic adjustment, in particular, the dynamics of the peripheral bulge, have been invoked as a mechanism to explain observed changes late in the last glaciation phase from 40 to 15,000 years ago. So we're going to see how these observed changes fit into sort of what we know about ice sheets over the last glacial cycle. So, so in the Hudson River, there's evidence for an eastward diversion around 40 to 30,000 years ago. And so the channel had, this is now submarine, but there's evidence that the channel, its previous channel was abandoned. In the Delaware River, near the mouth of the Delaware, there's evidence for increased deposition from 40 to 25,000 years ago, and this was based on rates of accumulation in sediment cores. And in the Susquehanna and the Potomac rivers, here there's evidence for increased erosion around the same time, starting around 30,000 years ago. And this is based on cosmogenic dating of strath terraces. So we're going to see how these changes fit in with what we know about ice sheet changes over the last ice age. So I'm plotting the timing of these observed river dynamics for each of these rivers, where the x-axis is time. So the right is the last interglacial and the left is present day. And I'm superimposing a global ice volume curve from the benthic oxygen isotope record from Lasiki and Rainbow. And so we can see that these data lie right before the last glacial maximum, near 26,000 years ago. However, we know that there are large uncertainties associated with mapping oxygen isotope values to global ice volumes, and the geologic sea level record can give us better constraints. So in the last several years, there's been work done to better refine estimates of global ice volumes during periods of relative sea level high stands in the last glacial cycle. In particular, I've worked a lot on MIS3, so this time period here right before the last glacial maximum. And so these more recent constraints suggest much higher relative sea level high stands during the glaciation phase compared to estimates based on oxygen isotope records. And so we can see that the timing for these changes in river dynamics now coincides with a very large drop in global sea level. And there's reason to believe that much of that drop in global sea level is due to the growth of North American ice sheets. And that's based on some work by me and led by others, showing evidence for ice-free regions in Eastern Canada, as well as analysis of glacial isostatic adjustment using sea level records on the United States East Coast. And this work suggests that the Laurentide ice sheet, especially the eastern sector, started growing rapidly starting around 45,000 years ago. So we can see that with these newer estimates of global ice volume and what we know more recent understandings of more recent constraints on the growth of the North American ice sheets, we can see that the timing for this change in river dynamics coincides with the time where there might be a rapidly growing ice sheet nearby these rivers, or at least these rivers would be on the peripheral bulge of a growing ice load. So now that we have more refined predictions for glacial isostatic adjustment in the glaciation phase, we can ask how a late growth of the peripheral bulge would affect rivers along the US East Coast. So we're going to use these predicted changes in topography to calculate how QC, or sediment transport capacity, might change in rivers along the US East Coast. Sorry. We know that sediment transport capacity is proportional to shear stress, which is proportional to local slopes and catchment areas. So we'll look at how glacial isostatic adjustment can influence the transport capacity of alluvial rivers and the erosion rates of bedrock rivers. So we'll calculate changes to slope and catchment area using the predicted topography, and we'll determine if we expect sediment transport capacity to go up or down. So if it goes down, we might expect a trend towards more deposition as the capacity to transport sediment decreases. So we might expect a trend towards less incision or more deposition. And then if sediment transport capacity increases, we might expect a trend towards more erosion or less deposition. So I'm going to show you our predictions for the impact of glacial isostatic adjustment on river channel slope. And so here the color shows the change in magnitude, where red is increase, and the highest color is increasing, is essentially by a factor of 2, so 100% increase, and decrease would be 100%. So sorry, blue is decreased slope. So we can see that and this is from 36 to 20,000 years ago, so during the main growth phase of the peripheral bulge, as the Laurentide ice sheet is growing rapidly, we can see that there are kind of substantial changes in slope. And in particular, in the Potomac, we can see there's this kind of red spot near the area where increased erosion was observed. And in the Delaware, we can see that there is kind of this blue region in the lower reaches of the Delaware, and slope is reduced by 80%. So that's consistent with the trend towards aggradation. For the Susquehanna, that's not the case. There's no change in slope at that site where an increase in incision is measured. You can look at the change in catchment area due to glacial isostatic adjustment. So here I'm showing drainage basin boundaries at 36,000 years ago, so before the main phase of peripheral bulge growth, and then at 20,000 years ago after peripheral bulge growth. And we can see that for a few of these river systems, this is important, but for most of them, it doesn't change drainage area very much. So the biggest one is the Hudson, where the Hudson River's catchment area is substantially reduced. And this is on the right, I'm just showing the percent change in drainage area upstream at any site along the channel. So for most of these rivers, there's not a substantial change in catchment area. So we can then combine this by making some assumptions about how sediment transport capacity is related to slope and drainage area. And so on the left, I'm showing that slope change map. The middle is the drainage area change. And the right is QC change. So this is the predicted change in sediment transport capacity due to glacial isostatic adjustment. And you can see that the pattern is largely dominated by the slope change. So in terms of kind of comparing back to our evidence for the Potomac, the slope increase occurs where an increase in erosion is known to have happened, but that's not the case for the Susquehanna. In the Delaware River, sediment transport capacity is decreased at the lower reaches of the Delaware, which is consistent with that trend towards increased deposition. And in the Hudson, catchment area is substantially decreased, reducing sediment transport capacity. And so, I think I didn't include here that for the Hudson River, I'll actually refer you to a paper that focused specifically on the Hudson River, where I modeled river migration in response to glacial isostatic adjustment. So I actually am not talking about that here, but in terms of these other rivers, change in dynamics was shown that the glacial isostatic adjustment changes sediment transport capacity during this time period in a way that's consistent with evidence for increased erosion in the Potomac and increased deposition in the Delaware. And I've shown that both drainage area and channel slope, which are important for understanding river evolution, were significantly altered by glacial isostatic adjustment during the late glaciation phase, or the growth phase of ice sheets. And one thing that I think is kind of interesting to point out is that the fate of this change in sediment transport capacity, whether it's increasing it or decreasing it, is largely the kind of the biggest factor is the path of the river through this map of crustal deformation. So when a river is kind of cutting perpendicular to a change in uplift, to an uplift gradient, that's where you'd see the biggest changes in slope. And so those are the sites where you'll see the biggest slope changes, are kind of sites where the river's path is perpendicular to a uplift gradient. So with that, I will kind of conclude this section, and we can move to the next section of the talk. So we're going to turn to the other side of the United States, to more on the West Coast, and look at mega floods and the erosion of the channeled scablands in Washington, in the state of Washington in the United States. So the channeled scabland is a landscape of a series of canyons that are formed by dozens of glacial outburst floods from glacial Lake Missoula during the last ice age. So, glacial, on this map on the right, I'm showing glacial Lake Missoula is over here in the right, and there are outburst floods that at some points filled a dammed Columbia River. So this is glacial Lake Columbia, and then overflowed into what is called the channel scablands. And so these canyons are cut into the Columbia flood basalt on an otherwise uneroded, lusk-covered, on an otherwise uneroded, lusk-covered Columbia plateau. And so this channel network is highly visible even from space. So on the right, on the left, I'm showing kind of this aerial image, and you can see that there are darker areas, which are where these canyons or channels were cut, and the lighter regions are less. So I think it's really striking. It's kind of fun to work on a site, just looking at Google Earth from far away, you can kind of see where you are. And this is a picture of what this looks like on the ground. So these canyons are cut into columnar basalt, and so you get these kind of steep walls of columnar basalt. So these floods happened from 22 to 14,000 years ago, and I'm including this map of Native American people who lived on this landscape just to point out that there were people living here at the time who saw some of these floods, and stories of these mega floods are recorded in oral histories and legends. So scouring of the channel scabland likely occurred while the Columbia River was dammed by an advancing Okanagan ice flow here, forming glacial Lake Columbia. And flood deposits suggest that the Okanagan ice flow blocked the Columbia River from 18 to 15.5 thousand years ago, and at least 80 floods occurred during this time. There are two main channel tracks: Telford Crab Creek, which I'm showing in blue, and Shaney Palouse, which I'm showing in orange pink. And there are a number of outstanding questions that remain about how the channel scabland formed. For example, over these many thousand years, did flood routing change over time? Were these two main channel tracks, Shaney Palouse and Telford Crab, were they carved at the same time? And how big were flood discharges? Were different flood events different sizes? And knowing the answers to these questions informs our understanding of how landscapes are carved by outburst floods both on Earth and on Mars, as well as how floods precipitate abrupt climate events. And prior studies have not accounted for the role of glacial isostatic adjustment in answering these questions. So I'm going to ask whether glacial isostatic adjustment can help us to answer some of these outstanding questions. So as we were talking about before, glacial isostatic adjustment refers to solid earth deformation due to redistribution of surface mass loads as ice sheets grow and melt over the ice age. And the channel scablands are located right on the edge of the Cordilleran ice sheet, which means they sit on the ice sheet's peripheral bulge. On the left, I'm showing the schematic again of how this works. So as the ice sheet grows, the peripheral bulge is uplifted. But in this bottom image, as the ice sheet melts, mantle flows back beneath the former ice sheet, uplifting the region beneath the ice sheet and causing subsidence on the peripheral bulge. And so these rates of uplift and subsidence from glacial isostatic adjustment in this region on the edge of the Cordilleran ice sheet substantially exceed local tectonic uplift rates in this region. And so these rates are on the order of 10 millimeters per year, and you really get the highest rates because you're right on the edge of the ice sheet. So you're kind of right in this gradient between subsidence and uplift. And so I'm going to consider the role of accounting for glacial isostatic adjustment in flood reconstructions. So here I'm showing how glacial isostatic adjustment changed topography in the Channel Scabland region over the time of Missoula megaflooding. Sorry. I'm going to focus on these time steps, 18 and 15.5 thousand years ago. But the age uncertainty on the timing of Channel Scabland formation spans from 20 to 14,000 years ago. So we'll try to see if we can use glacial isostatic adjustment simulations to answer some of these outstanding questions about the Channel Scabland. And so here's the approach that we'll take. We'll simulate flood routing on topography corrected for glacial isostatic adjustment to first discover routing changes over time. And then we'll predict the relative timing of erosion in the different tracts. And finally, we'll try to improve flood discharge estimates. So we use the flood model ANUGA to simulate overspill from Glacial Lake Columbia. And on the right, I'm showing the boundaries of this model setup. So these green lines are inflow boundaries. So this is, we have flow input discharges coming through those boundaries. And we simulate floods within these bounds, and these dashed white lines are outflow boundaries. So water can come out from these. And here I'm just showing an example of flood evolution on the 18,000 year ago GIA corrected topography using an overspill discharge of 6 × 10⁶ meters cubed per second. So we can see that over the time period of the simulation, we start to get flow in both of these channel tracks. We can then use these flooding simulations to calculate the maximum bed shear stress based on the predicted water depth and velocity. And so that's kind of giving us a potential erosion power. So here I'm showing, on the left, I'm showing 18,000 years ago. So simulations on 18,000 years ago, the middle is 15.5 thousand years ago, and the right is present day. And I'm showing the maximum bed shear stress achieved during flooding simulation. And so just to kind of help you out on the differences between these, here on the left, I'm showing the topography change due to glacial isostatic adjustment for each of these topographies. And so we can see that at 18,000 years ago, there is more uplift to the east than to the west, whereas at 15.5 thousand years ago, there's greater subsidence to the west. So this is kind of the difference in these topographies, and we can see that at 18,000 years ago, we get flow in both. Sorry for the automatic thing. It's from, these slides are from GSA and they have the timing built in. So we can see that there's flow in both channel tracks at 18,000 years ago, but at 15.5 thousand years ago, flow is mostly in Telford Crab in this blue channels. And these are both in contrast to present day, where we get really similar flows between Telford Crab and Shaney Palouse. And this is due to this change in topography. So at 15.5 thousand years ago, there's more subsidence in this region that's putting more water into Telford Crab. And so we can see that if we plot the discharge in each of these channels, so the blue is Telford Crab, so it's this more western channel tract, and the red or orange pink is Shaney Palouse. And we can see that at 18,000 years ago, there's more discharge in Telford Crab, and this is amplified at 15.5 thousand years ago. There's almost no discharge in Shaney Palouse, and these are both in contrast to present day, where we get about the same flow or amount of discharge in both channels. So we can see that glacial isostatic adjustment changes flood routing at these different times, And that means there's a different potential to erode each tract at these different times during the time period of channel scabland formation, and not accounting for glacial isostatic adjustment. So these present day simulations are quite different. So what we're going to do now is compare these shear stress calculations to the threshold to erode basalt, and by plucking the diameter of blocks that we know were transported during these flood events, so of 0.1 to 0.8 meters size blocks, and so this critical shear stress is around 110 to 1200 pascals. So we'll see how our maximum achieved bed shear stresses compare to these thresholds. And what we're going to do is we're going to separate out the basalt eroded regions from the not basalt eroded regions. So we're going to use this map of kind of where there's loess and where there's basalt based on these darker regions to compare. So we're going to plot these distributions of shear stress, comparing these two channel tracks. So Telford Crab is going to be in blue and Cheney Palouse is going to be orange pink. And then we're going to look at basalt eroded regions in particular. So at 18,000 years ago, and I'm also plotting the cumulative fraction. So there's an empirical cumulative distribution function plotted by these lines. So we can compare these distributions of shear stresses to the threshold to erode basalt. Sorry. And so we can see that at 18,000 years ago, we would predict to erode both Telford Crab and Cheney Palouse. So we see there's a substantial proportion of areas that are above the minimum threshold to erode basalt. And at 15.5 thousand years ago, with the same discharge, the same input discharge in our flooding simulation, we would expect to only be eroding Telford Crab. So we can see that Telford Crab in the blue exceeds the threshold to erode basalt, but for Cheney Palouse, very few areas do. And this is in contrast to simulations on present day topography that predict eroding both Telford Crab and Cheney Palouse evenly. And so if we assume the present day topography, we would predict incorrect flood routing and erosional history. So we can then look at our not basalt eroded regions. So these are the primarily loess covered areas, and plot the predicted bed shear stresses in these areas. And so the idea here is this acts as kind of an upper bound, because we know that these less covered regions were not eroded to basalt. So they shouldn't exceed the threshold to erode basalt. And so for 18 Ka and 15.5 Ka, this fits pretty well. There's very few areas that exceed the the basalt erosion threshold. Whereas at present day, there is a substantial amount of areas in less covered regions that exceed the threshold to erode basalt. Okay, so we can kind of use our shear stress values in basalt areas versus loess areas to try to bound what the minimum spillover discharge should be, because that discharge should maximize basalt erosion in basalt eroded regions, but minimize basalt erosion in not basalt eroded regions. And so here I'm showing the predicted erosion scenario using the discharge of 6 times 10 to the 6 meters cubed per second. And so at 18,000 years ago, we predict erosion in both channel tracts, but at 15.5 Ka, we would only predict it in one of them. And we can kind of explain this difference by looking at spillover elevation profiles at each of these times. And so at present day, these spillover elevations are lower than they were at GIA corrected times. And so that's why you get a lot more discharge coming through, since there's lower spillover elevations. And at 15.5, it's hard to see this here because you can't see the difference, but there's lower elevations in Telford Crab compared to Shaney Palouse. And so we can conclude that at 15.5 thousand years ago, a smaller flood discharge would be required because you're only funneling water into one of these channel tracks instead of both. So this kind of gives us a sense of minimum discharges that are required to erode at different times during the time period of channel scabland formation. So I'm just going to conclude this section here so we can try to answer those initial questions. Did flood routing change over time? Yes, flood routing likely shifted as glacial isostatic adjustment changed topography in response to ice sheet melting. Were the main channel tracks, Shaney, Palouse, and Telford Crab carved at the same time? No, these, in contrast with previous simulations, these simulations that include glacial isostatic adjustment suggest that the channel scabland formed incrementally. And how big were flood discharges were different flood events, different sizes. And we think that earlier floods at 18,000 years ago might have been larger than at 15.5 thousand years ago, at least the minimum flood volume. So glacial isostatic adjustment can help us get new insights into erosional histories of landscapes. And so done this for thinking about the channel scabland here. And this is implications for the size of meltwater pulses that would enter the Pacific over the last ice age. So with that, I'm going to conclude the whole talk. So we just thought about, this talk kind of centered on how glacial isostatic adjustment can influence landscape evolution over the ice age. In this most recent section, we focused on megafloods, where we use constraints on ice age deformation to learn more about erosional histories of the channel scabland. And in the prior section, we showed that rivers might be able to record crustal deformation from glacial isostatic adjustment and eventually improve ice sheet constraints. So with that, I want to thank my collaborators and see if you have any questions.
Thank you so much, Tamara. So I've opened the chat, so you can add your questions there, or let us know writing an X or raising your hand if you want to ask your question in person. But while we wait, Tamara, I wanted to ask you, so you use this threshold, basalt threshold, but shouldn't you use a threshold for loess erosion, or am I misunderstanding something?
Yes, so the idea is that the threshold to erode loess would be a lot smaller than the threshold to erode basalt, and so the regions that are still less covered probably didn't exceed the higher thresholds to erode basalt. But I think there is room to kind of do more detailed work, because some of these regions that are less covered are what are called streamlined loess, and so there were, the floods did go over these loess regions, but they didn't erode all the way to the basalt. So, so you could potentially add more complexity where you compare the areas that eroded some loess and some areas that didn't erode any loess. So you could kind of dive into more detail using the threshold for loess erosion too.
So I think we have a number of questions. Philippe, do we have an overview?
We have two raised hands from Eric Barefoot and Witang. I think maybe Vivi, you need to give them the access to the mic, or you are muted, Vivi.
Yes, great. I just have to find, so we'll take first.
It was Eric Barefoot.
But Eric, he put his hand down, perhaps. Okay, here, now I see it. So I'll ask you to unmute. Eric?
Oh, there we go. Okay.
Yes.
Yeah, I was having issues with that. Thanks for a great talk, Tamara. I was curious about the the way that the variability in slopes that occur in the rivers when you apply the glaciostatic adjustment on the East Coast. So in addition to just having, sort of broad scale changes in slope, it's also sort of varies quite a lot up and downstream. So how much does that variability impact your predictions for the broad scale implications? Because some of that sediment could be sort of buffered in those zones or something like that. I was just curious because it looked like there's a lot of back and forth of slope adjustments along the stream.
Do you mean the change in slope due to GIA, or the initial slopes in those rivers, or like the present day slopes in those rivers? Or you mean the GIA slopes, right? Sorry.
I just
Eric, did he get muted again?
I remuted myself because I was done talking, but yeah, I can clarify. Yeah, so there was I guess the change in slopes. Yeah, change in slopes. Yeah.
So
there's some areas that increased slope and some areas that decreased slope up along downstream.
Yeah, and okay, I've been really having a lot of trouble today with my mouse, so I'm gonna try to go back to that slide, but maybe okay, I think I can now. Okay, so yeah, there's quite a bit of spatial variability in the slope changes, particularly in these more southern rivers. There's kind of that alternating color, and this is so in some ways, so I think you're on to what's going on here, is that in some ways this is a little bit of an artifact in the calculation, because these changes of slope are happening on very low slope areas of the channels that are when I predict river path at these two different times, at 36,000 years ago and 20,000 years ago, there's kind of changes in like the channel belt sinuosities are changing, and so you're getting a slope change because you're actually changing kind of what path you're on. So you're changing slope from time to time, like from the earlier time to the later time, because you're actually just changed sinuosity of like there's some kind of like lateral changes.
Oh, I see. That's interesting. Okay, so these are so low sloping essentially that there's they can sort of seesaw back and forth in space.
Yeah, exactly. Yeah, and so I think what's kind of interesting is that, in those areas you are making predictions for where you'd expect to see like lateral migration somewhat, but kind of and so maybe that's, rather than saying, oh, like this is like a slope change in the river, are you seeing changes in channel belt geometry over those time periods, and how might they be related to GIA? Yeah,
very cool. Thank you.
Thanks, Tamara. I think we have Wei Teng if he wants to ask a question.
Hello, could you hear me?
Yes.
So I actually have two questions. The first off, is very nice talk, thanks. So the first question I want to ask is about because if I remember correctly, is the paper published in Nature 2016, Isaac Layson and the Michael Lamb's paper, to kind of argue about this kind of, for the second part of your talk, for the Canada, the outburst flood part, it can be the discharge is kind of smaller than people think before. So if you use your method right now, compared to whatever they estimate, is going to be bigger or smaller?
Well, so the answer is that they're slightly different, because the study, the Larson and Lamb study, was in Moses Coulee, which is a slightly different area than the one that I'm modeling. So so it's a little apple to oranges comparison, but the effect is so my work does suggest smaller flood discharges, and in some ways that's because I use the same approach as Larson and Lamb, using erosional threshold for a minimum discharge rather than matching kind of high water marks, which a lot of prior studies do. So the answer is that it also is a much smaller flood discharge, and by about an order of magnitude. So the discharges that I predict, see if I can get here. The discharges that I predict in these channels, it's in prior studies, they're 10 times bigger than that in these same channels, and those are based on releasing a maximum flood volume from Glacial Lake Missoula. And so this is taking a similar approach to Larson and Lamb, saying, well, if you come from the erosion constraint, what's the minimum? Sorry about this timing thing, it's kind of annoying. What's the minimum discharge required to get to these threshold erosional shear stresses?
Thanks, it's very nice. So my second one is more ask your feeling on that is, do you think your research kind of can help to constrain how many water in the glacial lake before? I think it's also as a big argument on that as well.
Yeah, I think that, there's a few sparse shorelines around Glacial Lake Missoula that kind of give you a sense of the high stands. I think the biggest question is how much water comes out of it during these outburst floods. Is it, if you can kind of see these high stand shorelines, but there's not very good, there's not like many different shorelines. You can't really see how much volume drop there is each time, and each flood could be different size. So I think it does weigh in on what are the minimum flood sizes that could produce the landscapes that you see today, or at least be floods that are eroding topography. So I think it kind of gives them a minimum bound on it. And in some ways it does bound a maximum using that Luss threshold, because with discharges that are too high, I start to predict that you are eroding basalt in areas that didn't erode through Luss. So it does kind of give you some bounds on like likely flood sizes during those times.
Okay, thanks.
Great, thank you, Tamara. We have a first chat question by Jan Evans. What was the biggest change in overall fall of each East Coast river? And could you give that in meters, sorry, if possible?
The overall what? Sorry.
Fall in, I mean the elevation fall, I guess.
Oh, so in what I showed was from over this kind of 15,000 year period. So there's different ways to think about it, but in terms of how these rivers were responding over this time, I think it's helpful to think of the change in topography, over the time. So this is showing, so basically topography is increasing. These red regions are where elevation is increasing as the peripheral bulge grows. So this is, is this helpful to see this in meters? Is that good, or do they mean relative to today or something?
I don't know.
Okay.
I think it's a good answer. Yeah. Thank you.
Next, we have a question from Ralph Hogerud, sorry if I mispronounce your name, who first thank you for a clear and thought-provoking talk. Could you elaborate on the observations and assumption behind the GIA you calculated for the channeled cap blend?
Yeah, so I totally skipped over really the ice histories for both of these sections of the talk. The ice history that I use for the channel scabland simulation is based on work that I've done prior work that I've done using the Bering Strait flooding history to constrain the timing of saddle melt between the Cordilleran and Laurentide. So kind of one major feature of the ice history I use is that it has kind of a later saddle deglaciation than other ice histories. And then the other thing that I do is I basically take a different ice, like I take an existing deglacial ice history and I modify it to include these ice lobes that are at the southern edge of the Cordilleran ice sheet and make sure that the timing of these lobes advance and retreat are consistent with geologic evidence. So most ice histories using GIA modeling are not really paying attention to those lobes because they're usually not trying to model GIA right next to the ice sheet. So that's something I do is I modify that geometry to match geologic evidence for the advance and retreat of those lobes. But I should say that I think that there is potential to there's still a lot of uncertainty in the ice history for the deglaciation of the Cordilleran ice sheet, and there's some potential to use new knowledge of the erosional history of the scablands to better constrain the deglacial ice history. So if we knew better the timing of erosion in each of these channel tracks, we might be able to kind of make some revisions to ice history that could improve GIA predictions too. And another thing I didn't say about the GIA is that I use a 1D Earth model, so assuming laterally uniform mantle viscosity and lithospheric thickness. And this is actually in a region where that might not be the best way to represent the Earth structure. There are changes in mantle viscosity and lithospheric thickness across the Pacific Northwest of North America. So that would be another improvement to the GIA modeling that I use.
Thanks.
Okay, let me take the next one. Yeah. So we have another question from Trevor Faulkner. Thank you for an interesting talk. Are there known relationships or references among max vertical forebulge uplift, distance from hinge line, and isostatic depression geometry in an adjacent ice sheet?
So I would say it varies from place to place. So depending on which ice sheet you're talking about, the thickness and extent of the ice sheet will influence the geometry of the peripheral bulge, as will the underlying Earth structure. And so it kind of varies a bit from place to place. Like, for example, in North America, where the kind of maximum part of the peripheral bulge is on the US East Coast is very different from what it is on the I should just say on the North American West Coast. Where on the West Coast, the peripheral bulge, kind of the peak of it is farther south than on the US East Coast. And that's because of very different mantle viscosities. There's kind of weaker mantle viscosities in Western North America compared to on the North American East Coast. So I guess I don't have a kind of a hard rule about it. It depends. But I guess I'll give you a reference for what I just explained there. There's a paper by Jessica Krevling, 2017, that is about looking at MIS 5A, 5C sea level markers on each coast and kind of showing this these different peripheral bulge gradients.
Thank you, Tamara. We have a question by Missy Epes. I think it refers to the first part of your talk. How far would you expect incision of these large rivers to propagate upstream for any given glacial period? And how long would that take to propagate upstream? And then she asked, do you expect or see evidence for effects in smaller channels? Sorry.
Great questions. So what's kind of interesting is that, well, I would say the answer is I don't know. But what's interesting is that these predicted changes in slope, you know, they're happening over relatively short time periods compared to what people generally think about for Nick Point migration. So, you know, slope is changing over 10,000 years during a time of ice sheet, you know, kind of rapid ice sheet growth. But then maybe the slope changes the opposite way during the deglaciation. So you're not necessarily getting kind of a long-term change in slope that you might expect to propagate. So I guess I would say I don't know, but I think we might think that the time scale for Nick Point migration would be longer than the time scale that these slope changes are active, because these slope changes are happening kind of differently, you know, maybe every 10,000 years or so, maybe even changing sign over a glacial cycle. So that might be my answer to that first part. And then in terms of smaller channels, I would say it's something I'm really interested in. I've kind of heard little bits of, you know, people that work on kind of upper reaches of US East Coast rivers that are thinking about glacial isostatic adjustment, but I haven't really dived into it. But I think that would be, interesting and possibly kind of an easier case studies where there's kind of maybe have less influences of, you know, big changes in discharge, or maybe that's not true, but yeah, I think it would be interesting to look at smaller channels too.
The next question is from Monghan Huang. Thank you for the talk, and I really like Geocontext. I have a question about the first part of the talk. In addition to changes of channel slope and drainage area, there is also a change of climate with precipitation. Mm-hmm. Could you comment on how this would influence your estimations?
Yeah, so that's certainly true, and also changes in, you know, sediment supply over this time. Some of these rivers their drainage areas drain the ice sheet, so they're getting, you know, different changes, you know, from meltwater, you know, changes in discharge from meltwater changes, or you know, kind of glacial erosion. So there are lots of other things going on. And so in that paper, we really tried to just say, well, what is GIA doing? But I think that is the natural question, is how does that compete with other factors related to climate change that are ongoing over the same time period? And so my understanding of precipitation changes over the glaciation phase, or even at any point during the last glacial cycle, is that, first of all, there's not super good quantitative estimates of it, especially for the US East Coast, but, you know, you kind of can get like qualitative changes. And I think it's reasonable to say that precipitation might have changed like maybe by 50% or so, not more than a factor of 2 or something. I think that more than that, people wouldn't really think is reasonable. And so I think like one thing that's interesting is that in some places on the US East Coast, the slope change is greater than a factor of 2. It could even be, you know, 10 times increase in slope in some locations. And so in those places, GIA might be more important than precipitation change. And so I think that's like kind of an interesting thing to think about. But yeah, that's your question. And it's something that I'm kind of excited about, thinking about how these different climate factors, you know, kind of what the to what extent is GIA important compared to other climate parameters?
All right, thank you, Tamara. I only see praises now in the chat.
Oh, thanks everyone for coming.
Yeah. So if nobody else has further questions, maybe we'll wrap it up here. But I thank you again, Tamara, for getting up early to entertain us all. Yeah, it was really great.
Yeah, thanks so much for inviting me. Let's see if I can.
Good. So yeah, I'm gonna, should I just close the meeting down, I guess? Yeah.
Oh, can I never got to see any of the sorry, I was just gonna, can I read the chats really fast now that I've closed my screen share?
Yeah, I can
Okay.
also perhaps Philippe can just send it to you.
Oh, okay, great.
After, then you have it.
Yeah, thanks so much.
And by the way, Tamara, I have actually a quick question just related to Europe. I was wondering if there are similar signals of GIA in Europe in terms of amplitude during the LGM or even before. And for instance, I'm living in Brittany, so the northwestern part of France.
Oh, cool.
What will be the amplitude of uplift, for instance, during the LGM? Do you have an idea?
I couldn't tell you off the top of my head, but it's not zero. You're definitely around the peripheral bulge there, so I think that is interesting, and a place that I have been thinking about but haven't worked on yet, but is kind of on my to-do list, is the Rhine-Meuse River in the Netherlands. That's a river where GIA has been invoked as a mechanism for changing, for causing avulsions or changing like deposition rates. So I think there is a potential to do this in Europe, and it's been on my list of projects that maybe Vivi even remembers me talking about it like a long time ago, because for a long time I've wanted to work on this, but I haven't. But yeah, I would be excited to think about rivers in Brittany too. Yeah.
So if you have some estimates for Europe, I would be very interested by that.
Yeah. Well, I can. If you want, I could send you like a figure from when I was looking at Rhine-Meuse stuff. I don't have it right here, but it would have some kind of estimate. So
thanks a lot.
Yeah. Cool. Well, yeah, thanks so much.
Yeah, good.
Trevor said yes, that 4 voltages are important. Yes, I think they are. Okay.
Yes. Good. Thank you,
Great.
Tamara.
Thank you.
Thanks a lot.
Yeah, and see you all.
Oh,
next
I'm still
week.
screen sharing. Oh, weird. Okay. Sorry.
Don't
Okay.
worry.
Bye.
Bye. Bye.
Bye.
Bye.